I traveled the world and gathered 3 test subjects. I questioned them on their height, weight, age, favorite color, how much they like cats, and whether they want to have children. With my newfound knowledge, I will start a business pitch, plotting height, weight, and age on a 3-dimensional graph. Their favorite color will be the color, obviously. X's and O's will show if they want children, because I don't know how to plot check marks. And what can I use to represent how much they like cats? I know. I'll use principal component analysis. The purpose of principal component analysis is to find a different set of axes that we can use to represent our data. So usually when we're trying to talk about points in a 2D space, we would give it an x coordinate and a y coordinate, and this is saying the data point is somewhere along the x-axis and somewhere along the y-axis. But with PCA, we're trying to find a different set of axes. So u is going to be our variable here, and it's going to represent a set of lines, or more specifically vectors, that describe the set of axes that we're trying to find. So the set of vectors u is going to be a set of unit vectors, and they're going to kind of be like the basis vectors for the x and y plane. And the set of vectors u will describe a new set of axes that we'll try to represent points as. And instead of expressing points as somewhere along the x-axis and somewhere along the y-axis, we're going to try to describe points using PCA, somewhere along u1 and somewhere along u2. And like the x-y axes, they're also going to be obviously perpendicular to each other. In a dataset, we would choose u so that the set of axes u will be always ranked by importance. So u1 will tell us the most information about our data, and therefore u1 will be the most important axes of our dataset. And the way they're picked actually is through variance. So in this graph with the new set of axes, u1 and u2, we can see that u1 tells us a lot about our data. And by that I mean there is a lot of variation along the u1 axes. In contrast, u2 almost doesn't tell us anything. In fact, we could almost just throw away the u2 axes and keep most of our data anyways. And the idea of throwing away u2, going from x and y 2 dimensions to just u1 1 dimension, is the idea of dimensionality reduction. By compressing a higher dimensional dataset into a lower dimension, we can speed up any computations that we may want to run on it. Another benefit is that we can visualize the data easier. For example, if we had a 6-dimensional dataset and we ran PCA, compressed it into just 2 dimensions, we can actually just plot it on a graph now. Now that we've got the ideas, let's see how we can perform PCA on this example dataset. The first step is normalizing the data, and we do this by centering all the data around the origin and scaling up or down all the data until their standard deviation is 1. To start, we want to find the first principal component, or u1, the most important axis. Like the x and y axes, this axis should also pass through the origin. Being the most important, it should also maximize the variance between the points that are projected onto it and the origin. We can roughly estimate this by looking at the length of the portion of the line that variables lie on. It turns out that maximizing the variance is also the same as minimizing the error, or the squared distance between the line and the point. The Pythagorean Theorem tells us that the variance and the error should add up to some constant value, namely the squared distance between the point and the origin. So as one increases, the other has to decrease. Let's compare these 2 lines. This one passes very close to the points, so the error is very small. If we project all the points onto the line, we can see that there's a lot of variance between the points and the origin. On the other hand, this one is very far from all the points, so the error is very large. If we project all the points onto this line, we can see that they cluster around the origin, meaning the variance is also very small. The line that we are looking for is not the line of best fit in linear regression. The line of best fit tries to minimize the vertical distance, while our line tries to minimize the perpendicular distance. If we wanted to stop there and project all our points onto u1 to form a different dataset, then we could do that and keep most of the variance. If we wanted to keep going, we would move all our points in a path parallel to U1 until they're as close to the origin as possible. Then we would repeat the process. U2 ends up perpendicular to U1, which makes sense because axes should be perpendicular. If we were to run PCA on a 6-dimensional dataset and we took 6 principal components, all of them would be perpendicular to each other. To find all the principal components, we would solve a calculus problem to maximize the variance between the projected points and the origin. Luckily, things end up simplifying themselves, and we can find all the principal components in just 2 steps. We would first compute the covariance matrix of our dataset. If our dataset was a matrix X, with one row being one data point, then all we would have to do is multiply X transpose by X and divide by the number of data points. The second step is to find the eigenvectors of our covariance matrix. The eigenvectors are the vectors U, with the one with the highest eigenvalue being U1, the second highest being U2, and so on. Alright, I used PCA and compressed all my data down into 3 dimensions. I should have a very successful business pitch, right?